And okay, so I will start. I'm going to talk about quantum mechanics. I know that probably a lot of people here are not very familiar with quantum mathematical physics, but I want to present some recent results concerning topologies using in quantum mechanics, some new topologies, and new because there is a need for them, and they will be associated under the name of Wasserstein or Kantorowicz or those names like this. Camera doesn't work. Okay. So my talk is going to be is going to be non-technical at all, and I'm going to try to convince you that quantum mechanics, in fact, is obtained out of classical mechanics by a kind of dictionary, and I will make the point of presenting the object I'm going to use in this talk by saying that they are not obtained by quantization in sense of microlocal analysis, but they are just the quantum version of the same object, in fact. In fact, it's one of the features of quantum mechanics that quantum mechanics give you an equation, but it doesn't tell you what the Hamiltonian, for example, is, and you have to take the Hamiltonian for classical mechanics. So I will start by showing you why it's interesting to use other topologies than the one we got used to it out of a functional analysis. Then I will show you this dictionary, and finally I will start a quantum version of Wasserstein distance, which is not a distance, but which is a quantum version of it. And I will show you how this allows, among others, to define optimal transport, but also something more general, like, for example, mappings, because the quantum mechanics is kind of a structure very rigid. For example, you cannot perform change of variable in quantum mechanics. It's something that it's unnatural for it. So I will tell you how this result allows to do it. Also, I will talk about the quantum version of the Legendre transform, an object which is very important also in optimal transport theory. But I will also show you an incidence of quantum mechanics, classical mechanics. For example, I will show you how this new topology allows to recover the classical dynamics under the Cauchy-Lipschitz paradigm, so to speak, which is a natural one, which ensures uniqueness, existence in uniqueness, how you can get it as a classical limit of quantum mechanics, and which is something new, because up to now, I will talk more precisely on this, merci. Up to now, you needed to have a lot of regularity in order to get this limit. And I will even show you some kind of perturbation result and stability of Cauchy-Lipschitz dynamics, so to speak, when the perturbation is not even under Peano stuff, that is not even continuous, just bounded. I will explain you that. And finally, I will try to exhibit some example where you can do things in quantum mechanics which are not possible to do in classical mechanics. In fact, quantum mechanics has been invented for that, and for the stability of matter. You can do it in quantum mechanics, you cannot do it in classical mechanics. For example, first to show you that the quantum optimal cost is cheaper in quantum mechanics than in classical mechanics. I will explain you why. And also a situation where you have a quantum Brownian theorem. I will explain what it is. In the case where you don't have Brownian theorems, in fact. This is true exactly because of the structure of quantum mechanics. So let me start by a very simple exercise in order to answer the question how to metrize the space of quantum states. Alors, by quantum states, I assume that everybody has a little bit of quantum mechanics in the head. In quantum mechanics, you have a Hilbert space, you have a vector in Hilbert space, and you have an equation which ensures the evolution of this vector in Hilbert space. Very often, the Hilbert space is an L2 space, and if you take a state like this, that is, this is a function of x, which is basically like a Gaussian like this, on which you vary the narrowing of it, like this, And as soon as you have this kind of object, which is very familiar in quantum mechanics and very useful, don't say what, you asking the question which distance between this pinned up near point Q1 and this pinned up with near point Q2. So the first reflex when you have the culture of quantum mechanics is to compute the L2 norms of the difference. After all, they are both in the L2 space. So what is the L2 norm of the difference? This is a fully explicit computation, and you get this square root, 1 minus another Gaussian expressed in the difference of the two positions you took, divided by epsilon. So you see that when epsilon goes to 0, epsilon could be the Planck constant, but it could be any parameter, in fact. If you look at a limit where your state shrink near point, what you get is that, in fact, you get that this is either 1 if this is strictly positive, either 0 if this is 0. So you get, in fact, only two for you distance between those two states, get only two values, 0 or 1, depending on the fact that the two states are the same position or the two states are two different positions. So it's something extremely stupid in a certain sense. You get the discrete, just a discrete topology in space. So you feel, of course, that something is missing, because two states like this, whatever the narrowing they have, should be differentiated if they're here or here or here. You know. So if you just think, so if you just make this very easy computation, we tell you that the L2 difference of the difference to the L2 norm of the difference of the vector is nothing else than the Hilbert-Schmidt norm of the two projectors on each state. And I want to emphasize this notation because I cannot avoid using it. Also, it's very quantum notation, but it's impossible. So it is due to Dirac. And by this symbol here, I mean just the orthogonal projector on the vector psi, when psi is number 1. So this is just a notation, but it's extremely practical. So this equality is very easy to prove. And so here you have the difference of two operators, which are called density metrics because they are pure state in this case, but they can be any, this operator. The main property is that it's of trace 1 and it's positive. And in fact, the state in quantum mechanics can be any operator which is positive of trace 1. It's exactly when you look at a dynamical system or Liouville equation, or that you take positive functions, your density is positive, and is of norm L1 norm 1, which is because you have conservation of something at this point. So the quantum Wasserstein, I'm going to show you just in a few seconds, ensures that now if you can, I'm calling MKM for Kantorovich, so this now evaluates the distance between these two now projectors on two space states pinned up at Q1 and Q2 will be now around Q1 minus Q2. That is, you get something extremely more refined because now you're sensitive to the distance to the point where you are. Okay, so of course we don't publish so many papers by this computation, but there are a lot of other properties, and I'm going to show you some of them. So the way I would like to construct this quantum Wasserstein would be that to do it through quantization in mean of corresponding quantum objects to all the parties which are entering the definition of Wasserstein, classical Wasserstein. And to do that, I have to give you just a dictionary to pass from classical word here to quantum mechanics here on this side. So as I tell you before, function, I think everybody has heard about that, a function in classical mechanics becomes an operator acting on a Hilbert space, this one. Positive function gives rise to positive operators, which has a meaning. If you have a function of one variable only, that is if I call Z1, Z2, a point in R2D, if you take a function which depends only on one variable, I get this on the tensor product. If I take another one, I get something like this on the other, on the same tensor product. And the main part is that what is the integral of A of Z dz, which is very often, because exactly, most of the time considers invariant or conservation properties. Oops. Okay. Then integration of a function corresponds to taking the trace of the operator. The integration of the product of function of two functions corresponds to the trace of another operator, and the integration of the product of two functions corresponds to the trace of the product of A1 and A2. It stops at 2. If you take the integral of 2, the product of three functions, it's not equal to the trace of the product of the three. Anyway, what I need to finish is that I will call Z a point in phase space. Alors, why is a phase space? That is position and impulsion, because quantum mechanics lives only if your classical dynamics underlying your quantum dynamics has a structure of a phase space on which the flow is given by a Hamiltonian function. Nobody knows what would be the quantum mechanics of some flows which wouldn't be Hamiltonian. This is why it is, I don't know, but it's really a difficult question and nobody knows. So, in fact, to this set of variables Q and P would be associated for Q the operator of multiplication by the variable, and for P the operator of minus h bar gradient with respect to the variable. These are the Q, really the fundamental objects of the quantization. And also, if you take the Poisson bracket of two functions, if one is just this operator, it should correspond to the commutator divided by A over h bar. So, if you understand this, in principle, you can do basically all the quantum mechanics you wish. And let us do now the translation. So, through this dictionary. So, I remember you that the Wasserstein distance between two probability measures, mu and nu, is given by this square, which is supposed to be the infimum of a certain integral. This integral involves a cost function, which in this case you take q minus q prime, p minus p prime, multiplied by pi, which is a measure on the double space. And this pi is supposed to couple mu and nu, which means that if I integrate over the two last variables, q prime and p, I got mu, the first one. And if I integrate over the two first one, I get nu, which is the second one. You can talk about conditional probability, you can talk about marginals. It's a definition of what a coupling between two measures is. And you integrate over this cost function, we coupled the two sets of variables in this way. I could motivate this definition going back to Monge problem and all that. I will not do it because it's not the main subject of here. But let us take this definition for granted and let us try to imagine how we could find a quantization of this. First of all, as I mentioned before, two probability densities should be two operators on the Hilbert space, which are positive and of trace 1. Secondly, the integral, which is here, should be a trace. Secondly, a coupling of mu and nu should be another density matrix with the property that if you take the partial trace with respect to the second factor, because this should be a density operator on this tensorial product, if you take the partial trace with respect to this second factor, you get R. If you take the partial trace to correspond to this first factor of this tensorial product, you get the second one. This is the equivalent of the case that you integrate over the second variable or integrate over the first one. So this gives you a definition of coupling. And the cost should be the function that we had before, that is this one. And you just now make the transformation which associates to q and q prime the multiplication by the variable. Here there is an rdx and rdx prime. And you transform p and p prime into the gradient, the nabla operator, the gradient, yes, with respect to the two variables also. So if you have this, all this, you get easily that you get a definition that you will call the Wasserstein distance over the two quantum 1 as the infimum over all the coupling coupling R and S between the two U2 density matrix of the trace of the cost times the coupling. You see, I hope everything sees the link between these two. You see, you have a trace which corresponds to the integral. You have a coupling here which corresponds to this definition and the coupling here. And you have the trace and you have the product of a cost times the pi. So this is the definition we take. This was not the first one, the first definition of quantum Wasserstein. There were several others. For example, the one of Zyslovsky and Stromzinski, another one by Carlen and Maas, related to, for people who know, to Benamou-Brenier theory. Another one by De Palma and Trevisan, related, and Ikeda also, related to some object coming from computing, quantum computing. I must say, not to make the publicity, but our definition in a certain sense, and this is how I motivated it, is the simplest one, I mean the one which fits the best with the classical one. When you take the classical one, the definition, you have a dictionary, you apply the dictionary on all pieces of your definition, and you get this one. So this kind of quantum Wasserstein has been used, as Mario was saying a few minutes ago, in order to prove some kind of mean field approximation uniform in H bar. It's not at all the direction I want to take. And I want first to study it by itself. You remember that I call this a distance, a Wasserstein distance of order 2. I didn't pronounce the word distance of it, and the reason is because it is not a distance. Alors, this is not a distance, but it has a flavor of a distance in a certain sense. Alors, first of all, you know, it doesn't satisfy exactly the triangle inequality, which is one of the axioms of a distance. You get something which is almost there because you get something, you have an additional factor here, which is the same for all the density matrix you have here, which is just D, which is a dimension, and H bar, which is a Planck constant. Of course, you know, H bar depends, the matrix, it depends on H bar because of this H bar here. So you get something which is almost a triangle inequality, and I must say that all the computation you succeed doing it with this are based on the fact that you compute things which are almost equal, but there is still a little bit of H bar which appears somewhere, but which at the end doesn't matter so much. That is, you release a little bit the fact of being strictly triangular, and you win a lot of things, I would say. Now, secondly, if you take the distance is bounded, for any RNS, is bounded by 2D times the Planck constant. This comes from the fact that you see this operator here, it's like a harmonic oscillator, and for those who study a little bit of harmonic oscillator, we know that harmonic oscillator has a fundamental of the spectrum which is not zero, but with something over the H bar. This is how Schrödinger wins the Nobel Prize, because Schrödinger got this Maslov, so to speak, Maslov factor that Heisenberg didn't have. Anyway, so you get this, and also, but still it separates points, in the sense that if it's equal to the minimum, so of course you could say, well, that's fine. I'm saying I just subtract to this the 2D H bar, and I will be fine. It's partly true, because if you get the minimum, you get that the 2 RNS has to be equal to 0. So this is an obligation, it separates points. But as a contrary, it can be strictly bigger than 2 H bar without having or different from S. That it is separate, it is a minimum, obviously, or is equal to S, but otherwise you can have density matrix for which the distance between the density matrix and itself is still strictly positive and it's not zero. This is a point. What you can do, and this is a work in progress, you can try to imagine what are the density matrix for which this is exactly the minimum, and you get some kind of a set of density, a certain density matrix, which are important, and I hope in this direction to get some kind of gradient flow and things like, so to speak, Otto, Benamou, Bernier did in the classical state. Okay, so this is the main property I would say about this. And now I'm going to show you an example of a computation that you can get completely, and we'll show you that for the same system, the quantum cost, that is the value of the quantum Wasserstein, is strictly smaller than the value of the classical one. And I will give you an explanation very easily. So very quickly, because probably I don't have... tu as quelle heure, s'il vous plaît?
C'est 3h04.
3h04. I have to hurry a little bit. So what is bipartite matching? You suppose that you have two particles here and 2 points here. First, you could suppose that they have an equal mass, and you try to pass the mass from this one to the upper one. Of course, if the mass is equal, it's very easy. You do that on one. You do the same on the other, and that's fine. Now, if you have different masses, for example, if the mass here is bigger than this one, what you can do is to propagate part of the mass here, then you propagate the rest of the mass to the first one, and because the total mass was the same, then you finish by taking the rest here into this. So you see that this is very nice, this way of transporting, but this is not a flow. This is not a flow because you associate to a single point here, this one, 2 points here. So it's not bijective, you know. No, not only it's not bijective, it's even ambiguous. So these are the two diagrams. Now, how do you implement this computation in terms of the Wasserstein distance? You associate it to a state mu to the one which right here by saying that you have two delta functions to measure two Dirac masses at x1 and at x2, ponderated by the masses like this. Here you have the one here on nu, same, and you can compute the W2. At the quantum mechanical level, what do you have? You have two density matrices, which is R, which is the sum exactly of the function, this Gaussian I introduced before. And here you have a projector on this. Here you have a sum of two projectors on the state, the Gaussian state I had before. The same for S, and then you can compute this. And the result is, if you define the classical cost and the quantum cost as a value of the distance, of the Wasserstein distance is the classical and is the quantum setting, you get that if the masses are equal, you have the same cost for the quantum and for the classical, but if the masses are not equal, you have a difference of quantum, and the quantum one is cheaper. So why is it so? I don't want to make the computation. You can compute, in fact, exactly the optimal coupling in the classical case. And what you find is that for the quantum case, in the case of equal masses, you get that in a certain sense, the quantum coupling is a quantization of the classical one, very easy. And if you do now the same computation in the case of non-equal masses, we are able to find another coupling, which we don't know if it's optimal or not, but which slow down the distance to something which is smaller than the other one. So this proves, obviously, since the Wasserstein distance is an infimum, that the infimum is smaller than the preceding one. So these are kind of simple computation using a little bit MATLAB, but why is it so, in fact? Why can quantum cost be smaller than quantum classical? Well, just because the fact that the quantum coupling, the set of quantum couplings, is not at all in bijection with the set of classical coupling. It's a much, much, much larger space. And its much larger space is as much larger than the other one as if you take the tensor product of two vector space, this is much bigger than the direct product of the two Hilbert spaces. All this story is related sort of to entanglement. This is exactly the flavor of quantum mechanics, which makes that you have, and since you have a set of coupling which is bigger and that you take the infimum, of course the infimum has the possibility of being smaller. Okay. Very quickly, another application of this. I'm not going to write the theorem. This is obtained with François Goltz, and it will be published. It should appear soon in Indiana. The fact that you see, everybody knows the Liouville equation. That is an equation, first order conservation equation, for which the solution is a push forward of the initial data by a vector field, a flow associated to a vector field. At the quantum mechanics, you have a Schrödinger equation that I don't write, and you can say that you just pass from here to here by taking h bar equals 0 or h bar equal to 1. Let's pick that, and you can evolve with the Schrödinger and then go back when h bar goes to 0, and that you find something. And you find something that, in fact, it's a solution of Liouville also. If V is W in 1, 0, that is a vector field, the gradient of V is continuous. This has been done, for example, existence, well-posed solution of this has been done in a paper by Ambrosio, Liouville, myself, and other people. Sorry, I forgot all the name. That is, you have well-posed. But when you have this, when you are under Peano, that is, if the vector field is not even continuous, then nothing is known. Of course, you know that it's not, it doesn't have to be a uniqueness, but it's very difficult to find some kind of estimate on anything like this. And what we prove with respect to this quantum Wasserstein is that if you perturb a Cauchy-Lipschitz flow by something which is just Peano, it remains close to the first one at the distance square root of epsilon, and if it's not even continuous but just bounded, then the classical limit remains close to also to the solution of the unperturbed flow. That is, you get something that you don't know what it is, you don't know how it is related to Liouville, but you know that it still stays in a tubular neighborhood. I'm sorry, I don't want to spend much time like this, but if you believe that quantum mechanics exists, the true classical dynamics is one you get from here. That is, you are at the level of Schrödinger, and you let h bar goes to 0, so you get a dynamic of stability result for this dynamics. Anyway, so associated to classical Wasserstein distance is the notion of Cantor-Rogic duality. Probably everybody knows that better than I, because I'm novice in this field, which tells you that the same Wasserstein, classical Wasserstein distance, which is given by an inf, is also given by a supremum over all functions so that a and b is smaller than the cost of the integral of a with respect to the measure d mu plus b multiplied by integrated with the measure nu. In fact, under some condition on the measure mu and nu, this supremum is in fact a max, and you find that in fact you have two optimal potential, A optimal and B potential. We tell you that this square of the Wasserstein distance, which on one side is given by an inf over couplings, and this inf is also obtained, that is in fact is a mean over couplings, that you have an optimal coupling, is given as the integral of the cost times the minimal coupling, optimal, and it's also equal to these two integrals with respect to these two potentials. Now, the Brownian theorem tells you that, in fact, the support of the optimal coupling, which gives you the value of W do, is contained in a graph of a function of the form in the graph of a function which is a Laplacian of, in fact, of a convex function. That is, what you know about the P optimal is the fact that if you multiply by this function, it's equal to 0. In other words, the support is contained exactly in the graph of this function here. The graph of this function here. Alors, it's very important to relate this to the original Monge problems, but I'm very fast about this, but what I would like to show you is an exercise which answers what should be this in quantum mechanics. That is, can we guess with a dictionary what's going to be this formula here, which involves a density, so this should be a quantum density, a density matrix. This is the two variables, that's fine. This is an optimal, if we have kind of Kantorovich duality, this will provide you an operator here. And what is going to miss is, in fact, is the gradient, and what we have to define is what will be a quantum version of the gradient of a function. So I just said that everything was fine up to a gradient. And now I want to know what is the equivalent, the quantum equivalent of a gradient of a function that is an operator acting on another operator, since A now is going to be an operator. So the first remark is to say that the gradient of A is the gradient of QA, gradient of PA, of course, this is a vector. And in fact, what is the gradient of Q of A? It's a Poisson bracket of A with respect to minus P, where the Poisson bracket is this obtained out of the symplectic form you have on your phase space. I'm a little bit geometrical, but not so much. And the difference with respect to P, you look at this, and it's exactly like this first term here. So it's a Poisson bracket of Q, function G of equal Q, with A. So now we are in shape of starting to quantize this, because we have a Poisson bracket, and we have seen that in the dictionary, Poisson bracket should be quantized as a commutator. It's exactly what Heisenberg invented in 1925. Invited the commutator, he realized the importance of commutator, but it's Dirac who really understood that the commutator was a Poisson bracket. So, but here you have minus P and Q, so if you define this symplectic matrix here, you get that at the classical level, the gradient of something is just the Poisson bracket of G acting on the vector, canonical variable Q and P, Poisson bracket with the function you want to take the gradient. Now, if you have this, you quantize immediately, because the Poisson bracket becomes 1 over IH bar commutator, G remains this matrix, and then Q and P becomes multiplication by X and minus IH bar divided by the X. So if you look like this, then you have defined what should replace the gradient of A, and then you should have something like this or something like this, because remember that in the Fourier, in the Brunier theorem, you had that y minus gradient of A times the optimal coupling. And whatever you put the optimal coupling on one side of the other, since you have function of measure, it doesn't make any difference. But here, these are different because now we have operators here and there. And the answer will be given. I mean, it has to prove, and this is just to have a guess, but it has to be proven, and it was proven, is the fact that, in fact, quantum mechanics, it's a general rule, it prefers symmetry usually. So how do you do something which is behave a little bit like this and a little bit like this? You just put a square root on both sides, and it's something which looks like the same. It's the same if everything was commutating. And the beauty of the thing is that this wouldn't make any sense in classical mechanics, because how do you take the square root of a probability measure? Or square root of a measure, you don't know what it is. But, of course, in quantum mechanics, square root of a density metric exists perfectly, because now you have positive operator, phase one, so the square root exists perfectly. So, in fact, what now the theorem is? The theorem is the fact that, first of all, we can do quantum Kantorovich duality in quantum mechanics. That is, you have formula which are exactly the same as we had before, once again according to our dictionary. The supremum is the max. It's the max about the optimal A and B are now a little bit difficult object in functionalities. They become Gelfand triples and not just bounded operator. This is all mechanism which is provided by the proof. We are not sure it's optimal. But anyway, suppose that you have this optimal operator, then we prove exactly that. That is, if you look at the optimal coupling between two density matrix R and S, you have that Z times I, which you see Z times I touch only one part of the factor. They touch only R part is equal to I times the gradient of A, which touch only the second part, that is a part of S. That is, in fact, this is equivalent of having X is a Y minus the gradient of A of X, because X and E are related to the two density matrix. Well, anyway, you do some computation like this, and in fact, what you get out of this is just the fact that if you take the trace now, the full trace of this, you see that since here you have something which is the identity here, in fact, it's very easy to see that the trace of this part is just equal to be the trace of Z times the partial trace of the coupling, and the partial trace of coupling by definition is R. So you get the trace of Z of R is equal to the trace of the gradient of A times S. Of course, you could imagine that this is very unsatisfactory because it doesn't tell you so much, because you have just taking these averages here. And in the next slide, I'm going to show you that in fact, well, first of all, I will not show you, but if you do the computation, it's easy to see that you cannot get something more precise than this. That is, you cannot get rid of this average phenomenon, which is including in this trace formula. Because you have, if you would like, for example, that you have only this part of the equality without reprojecting here by this coupling here, then there is no solution of this. No solution, because the eigenfunction, which are the eigenfunction of this pi here, should satisfy too many conditions with involving too many operators. We don't commute itself, so it means that it's just impossible. So, except some trivial cases where you take the same R and R or something like this. So in fact, the fact to have the trace like this is something which seems to be a little bit optimal, but it's also very much in accordance with quantum mechanics. And this is a movie which started. You know, in quantum mechanics, you have a wave function, and you have an evolution of wave function by the Schrödinger equation, and you have also another part of the dynamics, which is the famous measurement process. That is, if you take an electron, if you ask to the electron, it stopped? Oh. No, it doesn't stop. Yeah, it just wait. So if you measure the position of an electron, it can be any point on the screen, for example, because this is an experiment screen, because at each measurement, you have a totally random result. The only thing you know is that if you do a lot of measurements of the same electron, or at least the electron is the same state, then you will get some structure like you have here. And this structure is just given by the fact that the wave function of the electron, before the electron touches the screen, has been passed into two small two slides, two small slides like this, you know. That is, if you can do with electron exactly the same experiment that you do in classical optics, you get exactly this this kind of structure. Yeah, I have to do that and that, which will appear here again. But now this structure appears not only as a density of electron or something like that, it just is a density of probability of getting the result. So in a certain sense, if you want to send your wave function to some mapping, to something like this, it's impossible to say, I change the variable, mostly also because this kind of transformation from Z, which is a point in phase space, to this new position, is a change of variable, but in phase space. And this probabilistic interpretation works only in configuration space. You cannot do anything else morally than to take just averages about measurement And this is why you get exactly what I was doing before. So finally, we call the paper with Emmanuel and François towards optimal quantum optimal transport. But I think the right title is really quantum optimal transport. It's not towards, it's really the best we can do. We cannot get more than this.
Sorry, this is experimental evidence.
So this is an experiment doing in what was called at that time Cachan École Normale Supérieure. And this is really, so you see the experiment is you let one electron by one electron passing to the wall where you have these two little overture. Of course, it's not the same electron, but it's all the electrons we pass are exactly in the same state. And in fact, in quantum mechanics, it doesn't mean anything to say that you have the same electron. The important fact is just the state on which it is. And the beauty of quantum mechanics is that because it's quantum, because it's something discretized, you can be sure that you have exactly the same state. If you were in classical mechanics, you are never sure that the positions are equal because you have a power of continuous between positions. Here you have discreteness, so you can be exactly sure that you have the same state, that it is the same electron which passes, and you see completely random effects. But if you do it, I don't know how many times here, maybe 100,000 times the same over here, then you get that, this kind of thing. Okay. So just very briefly to tell you a little bit of the proof that we have, which in fact I believe induce a new proof of this theorem. I come back to the classical Brownian theorem, that is the fact that this is equal to 0 on the support of P. And I'm not sure that this is really a complete proof, but morally it's exactly, it fits what you have. You see, you have this condition like this, which is exactly the condition that you have in the Kantorovich duality, the fact that you take the maximum, but you need a constraint. And this is exactly the constraint. You take the maximum over all the A and B in such a way that this is bigger than 0. And what you prove is that if you are exactly, if you take the optimal A, B, and P, you have this which is equal to 0. Why is it equal to 0? This part here, with respect to P, is the first definition of the Wasserstein distance, the square root. Now, A of x integrated over P of dx dy is, you can perform the integrate over y since A dependently on x, and you get exactly the first measure mu. So this is the sum of A integrated with respect to mu we had in the Kantorovich stuff, and the same here for nu. So in fact, you know that you have this. But since this is positive, and this is positive, the fact that this is equal to 0 tells you that all that is equal to 0, right? Because you have the integral of a positive function which is equal to 0, the positive function has to be equal to 0. And this means that you have this, which is 0 on the support of pi. Or in fact, just take this one here, and suppose that I let the gradient, that is a derivative with respect to x. What I will get here? No, the fact is the following. You have a function which is 0 on the support of pi, so that is the support of pi is a place of a minimum of a function, and this function is positive. This means that the gradient must vanish, right? If a function is positive and it has a minimum term y, and deriving this, you get exactly this formula. So I'm not completely sure because, of course, you would have probably to derive also pi or something like that. But in fact, in the spirit, is exactly the philosophy. The proof usually, if you look in the good textbook, is done with subgradients and things like this. But the idea is this, and it's exactly what works in quantum mechanics. In quantum mechanics, we have exactly the same thing. We have something which is positive here, and we have the trace with respect to pi 1/2 and pi 1/2. I redistributed the pi 1/2. In principle, I have just pi here, but I redistributed here because I have a trace. I can do this, which is equal to 0. This means that this operator is equal to 0. And now, if I take the square root and blah blah blah, I have finally that this is equal to 0. Believe me, it's just a very easy computation. And now if I let the derivation acting on this, I will have the derivation acting on this part times pi times this times the derivation acting on pi. And now the question of having something fundamental in the support and all that doesn't work anymore because I have only operator. So the only thing is that you have this. But now if you remultiply by pi on this side, you cancel the part where the derivation was acting of this because this times pi on the other side is equal to 0. So this is why, in fact, you get this. I forgot the 1/2 because it's the same, of course. I got this with the 2 pi, which is distributed on the two sides. This comes only from the fact that you don't know what the derivation acting on pi is, and you do this with respect to this. So I believe this is full proof of Brogniar's theorem. Now, I went, what time is, Roberto?
12:30.
12:30. 10 minutes more, that's fine, or 15 minutes more? I think we started at 20 minutes, okay. So just to try to make you a little bit relaxed, this place, I call it an Italo-Trenitalia type alternative view. Why is it so?
6 o'clock then, if you use Trenitalia.
Yes, maybe. But if I remember when Italia didn't exist, the first time I came to Rome, for example, what was the way of using a train station? You were going to a train station, you were saying, I want to go from Rome to Naples. And the lady or the man was saying, very nice, I send you a ticket to go from Naples to Rome. Now if you do that on the webpage of Italo, you cannot do that because they were going to tell you, why do you want to go from Rome to Naples? Go from Bari to Milano, because here the billet is less expensive. It's more cheap, you know. So in fact, they transform the fact that you wanted to fix the two extremity of your travel by the fact that you take a travel, whatever it is, but it's cheap, you know. And this is where people travel so much. It's a little bit an analogy with geodesics, that, you know, instead of seeing the 2 points, you look at just what is the geodesics independently on the way it passes. So the theorem is the following. Instead of starting from 2 density matrix, take for granted 2 operator B, self-adjoint, bounded, in such a way that the cost minus Z minus C is the cost, Z is positive on the domain, forget about that. You remember that it was exactly the constraint we had for the Kantorovich duality. So suppose you have this, and suppose that the kernel of this operator, which is positive, is non-trivial. It's not the empty set. It's any kind of, it's a vectorial space of dimension maybe infinite, maybe just 1, etc. And suppose that you take a pi, which is a bounded operator on this bounded and positive or trace 1. That is a coupling of something, but you don't know the something, in fact. It's a coupling. Then, what you can prove is that if I take the 2 marginals of pi, that is if I now some R, some S, so now this is Bari, this is Milano, and this is a cheap train in my image. So the result is that if I take any density matrix which lives on this kernel, then it's an optimal coupling of its marginal. Of course, it's a coupling of its marginal. That's totally tautological. Any coupling is a coupling between these 2 marginals. That's the definition of a coupling. But now it's an optimal coupling between these 2 things. This means that you can define, in fact, with respect to this, a mapping which starts by R, which is the first marginal, and end up at S, which is the second marginal. And this is why I wanted to say like this. That is, you define this, and in such a way, you define a mapping which goes from any density matrix, which is a trace with respect to the second variable of a pi, which belongs to this density matrix in this kernel, and send you in order to S, and you have this property. Because you see, I told you that this property was a kind of weak property compared to what we would like to have at the classical level. But it's not at all obvious to find a transformation which passes from R to phi of R in such a way that this is preserved for a large set of R's, in fact. It's not obvious at all, and optimal, this kind of quantum optimal transport give it to you. Okay, so I should hurry up. Very briefly, this finite dimensional case, sometimes this kernel or the RNS can infinite rank. This was exactly the case for the bipartite matching, in fact. And in this case, in fact, you can prove that this corresponds to measure mu and nu, which are singular, and that is are two singular in such a way to satisfy the hypothesis of the Brownian theorem. So for this kind of very singular probability matrix, you cannot find a transport. And here, in fact, you can find a transport. This is given by something like this now, and I have no time to develop here. But just the morality of this is just the fact that in quantum mechanics, you do something like this, although in the classical equivalent, you cannot do it. That is, you have a kind of quantum Brownian without classical counterpart. Okay, so now in really 5 minutes or 10 minutes, I would like to introduce a new kind of distance, and the philosophy will be the following. You remember that in order to pass from classical Wasserstein to quantum Wasserstein, we quantized the two mu and nu into two density matrix RNS. Suppose now we play the role of quantizing only one of them. That is, you quantize only mu, which gives you quantum density, and you keep nu as a density, a classical density. In principle, the dictionary will give you something. And this way, you will have a distance which now will fail even the last things, the last axiom of a distance that was satisfying the first one. That is, you cannot invert the two points because the 2 points live in two completely different spaces. But still, you can do it like this. And by this, you can get what I make a resume on this slide, which I think it's interesting if you think about a semi-classical limit and transition from quantum to classical. First of all, in this transition from quantum to classical, there is a kind of paradox, is the fact that in order to the classical dynamics to be well defined, you need Cauchy-Lipschitz condition for the vector field, right? To be uniqueness. At the quantum level, you don't need any regularity. For example, consider Schrödinger operator with a potential which is just bounded, whatever it is, its regularity. You still have the dynamics, the operator is self-adjoint, etc., etc. And in fact, when you pass from quantum to classical, you need a regularity which is quasi-infinite. All the methods we have up to now were doing this. You need a lot of derivative of the potential to be bounded. And the reason for which it was, so for people who know, is the fact that you have to use Calderon-Vaillancourt theorem. That is, at one point, you have to estimate a remainder, and you have to estimate the remainder. You know its symbol, you have to estimate this remainder, which considers a pseudo-differential operator, and then you need to use the Calderon-Vaillancourt. And Calderon-Vaillancourt is very regularity consuming. In fact, especially if you increase the dimension, the number of derivatives you need is increasing very fast, and the constant, which gives you the precise estimate, also increases in principle very fast. So in fact, by doing this kind of semi-quantum Wasserstein that I'm going to define now, you get that the semi-classical, the classical limit is valid only or also for potential which satisfy Cauchy-Lipschitz. So in a certain sense, it's satisfying for this. And the reason for that is here I remember that in usual micro-local analysis method, you compute a quasi-solution of your true solution, and you have a remainder which is supposed to be small in h bar. But to estimate this, you have to estimate the L2, the bounded operator, the operator norm of this remainder, and this given by Calderon-Vaillancourt in terms of a certain constant which depends on the dimension, L2 of RD here, and the supremum over a certain number of derivative. So first of all, if you want a result which is valid for all dimensions, you need to be to be infinitely differentiable in V. But also, if you look at this CD, in fact, nobody looked, but we looked with Francois to estimate this CD, which in principle is constructive. We couldn't get anything better than the factor of D to the power 7. So it increased extremely fast. Even if it is equal to 3 already, you have a huge constant. So the theorem we get has the following form. There is this distance here that I'm going to define now, and I compare directly the solution of the Schrödinger equation with the solution of the Liouville equation. And what I get is that this is bounded by the same thing as t equals 0 times an exponential factor. That is, we got a Grunwald type of estimate, which is completely different than writing that you have a solution which is something plus something you don't know. You get a Grunwald estimate or de Bruchin estimate, and this now involves only the Lipschitz constant of the gradient of psi, and this is why you are just in Cauchy-Lipschitz paradigm. Okay, so what it is, very quickly, this semi-quantum pseudo-distance. As I told you, I will now take some of the things that I'm going to quantize. That is, on one side, for S side, I'm going to have S and gradient of X quantized. And on the other side, I will keep the classical variable Q and P, and I will have a trace for the part which corresponds to this, and just an integral for the part which corresponds to that. You define this. You have property which is very close to the preceding one. And at the end, what you get is that a transport exactly as we had before. I have to hurry up. And just the fact that now what is a coupling? A coupling is the density of one particle which depends on z, that is, it is a function of z value in the density, since we quantize only half of part of it. And you find that the optimal function associated to the optimal operator in the Cantor individuality is in fact the lowest eigenvalue of B. This means that by variance-zonal characterization of lowest eigenvalue, you find that A of Z is the infimum over phi of B, the average of B in phi, minus Z, the average of Z in phi. And this is what we define the quantum Legendre transform, because it's something where it looks exactly like the formula here, except that you take a supremum or an infimum because you change the sign, with respect to now some kind of operator value here. And I think I should stop here. Yeah, this is work in progress, and so I'm going to stop here.